Hello and welcome back. We are on lecture 7. In this study, we are going to focus on principal axes and principal moments. However, for us to come up with those principal axes and moments, we need to find some parameter called the product of inertia. The whole idea with principal axes and principal moments is this. When we calculated our moments of inertia, we only referred to the XY plane on which some area was seated or was located. Now, in our analysis, we never figured out whether this moment of inertia is actually a maximum or a minimum value. We just calculated a value, we used the parallel axis theorem, and so forth. However, you'll find that the moment of inertia is a physical property, which is the resistance of a body to rotational speed. Now, if that's the case, there are certain orientations, obviously, because we are talking rotational speed. There are certain orientations of axes which, when you analyze, you will find that that body has got a higher moment of inertia than the other. Try it this way. Look at an area, it's vertical, it's a rectangular area, and then you calculate its moment of inertia about the x-axis. And then the same rectangular area, rotate it so that it is now oriented on its length. Then calculate moments of inertia about the x-axis. So when you carry out that exercise, you will notice that orientation actually affects the values that you're going to obtain. So for us to obtain a certain maximum or a minimum, or to actually find the range in which the moment of inertia lies, then we need to find what are called principal axes. So generally, the principal axes are those axes or a set of axes at which the moments of inertia are found as a maximum or a minimum. In other words, on the principal axis, you can obtain the minimum moment of inertia. On the principal axis, you can obtain a maximum moment of inertia. So that will obviously be useful in engineering, obvious, because you need to see how easily you can rotate an object or how easily you can apply a moment to a static object. So this principle will be necessary later on. Right, so for us to understand it, we will also use a tool called Mohr circle, and we'll see how we can calculate those minima and maxima using Mohr circle. So chapter 9.3 is entitled Transformations of Moment of Inertia. When we discuss transformations, what we're actually doing, what we're actually trying to do, is to convert our normal moments of inertia that we will have calculated on an XY plane. We will have calculated them using an XY plane. We want to convert these moments of inertia into some other system of axes on which we can easily locate the minimum and the maximum, and even calculate other moments of inertia at different orientations of the area. So the process of transforming our moments of inertia from one set of axes to another set of axes, right? To another set of axes. So this is now the x prime, y prime axis. That process of converting our moments of inertia to another set of axes is the transformation that we're trying to do. So in this case, our moments of inertia will first of all be defined in terms of something called a product of inertia. So that parameter is going to define, and it will add to the moments in order for us to find the principal axes and principal moments. So the first discussion is on product of inertia, and then on principal axes and principal moments. Let's investigate the product of inertia. The product of inertia is simply a product, right? So you've got a moment of inertia that we'd already defined, and we know that it's Ix is equal to y dA. Then if we have another product, which is Iy is equal to x squared dA, then we can find the product, which is Ixy, which is equal to the integral of xy with respect to the area. Now, as far as that integral is concerned, it refers to the same setup as we had before, where we have our object with some area A as labeled there. Then that object has some area element which we intend to integrate in order for us to find the product. The area element is located at some x position and some y position. So those are the bounds that we will use to then start our integration process. So that defines the product of inertia. Now there's a special property of the product of inertia that arises when an area has a line of symmetry. When an area has a line of symmetry or some axis of symmetry, then its product of inertia is 0. So that's a special property. I think by now you remember that if we have some area element dA and we have an area element dA prime that is exactly at an equal distance but in the other axis or in the negative axis, then if you were to find the total integrated moments of inertia, you get a 0. Same applies. If you were to find the product of inertia for those two area elements, they would add up to 0. So the integral will end up adding up to 0. So that's just a special property of the moment of inertia, product of inertia. If an area has a line of symmetry, then it has a 0 product of inertia. Now, one principle that we discussed is the parallel axis theorem. Fortunately, it also applies to the product of inertia. So if we have some yx system of axes and we have our area A, that area has some shape, some arbitrary shape, and that area has a centroid at point C. We can find the product of inertia of this area by simply looking at the parallel axis theorem. So just the same way as it was derived before, the parallel axis theorem for the product of inertia is described as follows. If we have an area element that is located at the x distance on the original axis, y distance on the original axis, we can analyze it with reference to the centroid C by labeling distances x prime and y prime from the centroid axis. So our centroidal axes are labeled x prime and y prime. For us to then find the product of inertia, we already have an equation, isn't it? So let's now relate the product of inertia of the whole system to the centroidal product of inertia, because that's how the parallel axis theorem works. So if you investigate this area, you should be able to see now that all we intend to do is to relate this x to the what? To the centroidal axis parameters. So as you can see, our x here is simply equal to the sum of the centroidal x plus the area elements x relative to the centroid. So that's x prime. The same applies. Our y is simply equal to the y bar plus y prime. So these x and y variables of the original axis are related to the centroidal variables using the following equations. X is equal to x prime plus x bar. The same applies. Y is equal to y prime plus y bar. So with these two equations, we can now express the product of inertia with reference to the centroidal product of inertia. How do we do that? We can simply come into our equation. Our equation says the product of inertia, equation 9.12, is given by xy dA, the integral. So if we integrate xy dA, and we now know that our x is a function of what? Of x prime and x bar. Then we can actually substitute. Our x, we noted that it's equal to the centroidal distance plus the distance from the centroid to the area element. Hence we have x plus x prime plus x bar. The same applies. The same applies on the y side. We have a y prime plus y bar. And then we're integrating this product. When we integrate, I think you should be able to easily see that we multiply our x prime by y prime, so that in the end we get the integral of that x prime, y prime with respect to area. When we move to the next set of variables, we have a y bar, and then we will integrate x prime with respect to area. The same applies when we do that. We are going to multiply x bar by the integral of y prime with respect to area. The last set are x bar and y bar, but these are constants. The centroid is a fixed position. So because of that, these constants are out of the equation the same way they were out of the equation here, so that we integrate dA to get the total area. So in the end, we have an equation that states that the product of inertia about the xy axis, the original axis, it's equal to the first parameter, which actually is in the same format as that equation. It's also an integral of an xy, but the xy that we are discussing is the centroidal xy. So therefore there is this I bar, which, if you still remember the parallel axis theorem, is for the centroidal moments. So in this case, this is for the centroidal product of inertia about the x prime, y prime axis. These two terms, what did we say happens to these two terms? If you still remember, we are integrating about the centroidal axis. So this is the first moment about the centroidal y-axis, which is x prime dA. So if you look at the centroidal axis, we'll always have elements on both sides. For that reason, we will have a 0 for this term, and the same applies, and these terms add up to 0. The last stage there is simply the product x bar, y bar, and the integral gave us an area. For this reason, we actually have a parallel axis theorem for products of inertia. When you're given some regular shape, therefore, you can easily just apply the parallel axis theorem. So now what do we have? We now have two tools. We now have the first tool, which is the product of inertia. And then we have the parallel axis theorem for the product of inertia. We actually have three tools. We know that we can easily eliminate the product of inertia if there is some symmetry on an object. So we now have those three tools to use. So let's use the tools. So in this question, determine by direct integration the product of inertia of the given area with respect to the x and y axes. So for us to find the product of inertia, I think we already know that if we have an x and y axis and we have a body, this body is at some height h and it's at some location b relative to the origin in the x axis. For us to find the product of inertia, we have the parallel axis theorem to make use of. What does the parallel axis theorem say? The product of inertia about the x-y axis is given by the centroidal product of inertia. This is about the x prime, y prime axis. So we can actually draw the centroidal axis. Centroidal axis. So that's our x prime, that's our y prime, and that's our centroid, plus x bar, y bar, isn't it? X bar, y bar, dA. When we look at this equation, I guess you can immediately tell that this is equal to 0. Why? Because we have some line of symmetry. So all the products of inertia at this location will cancel products of inertia at that location, and so on and so forth. So we will obviously get a 0 on that one, and in the end we just have x bar, y bar, dA. So then if we integrate both sides, this is xy. If we integrate both sides, we will have an Ixy, which is the product of inertia about the xy axis. This is equal to our x bar, y bar, and these are constants, and these will multiply the integral of dA, the integral of dA. Let's expand this. We will get an x bar, y bar integral of what? This is just going to give us an area, isn't it? This is an integral, because here we can't really start talking about the functions. So this is just an area. This is regular, so I don't need to think way too much. So now that we have that, let's just put in our variables. Let's put in our variables. So maybe let's just write here. X bar is what? Is half of b. How about y bar is half of h? What is the area? The area is b multiplied by h. B multiplied by h. So that gives us a quarter of b squared h squared. That is our product of inertia. Product of inertia. So that is a useful calculation. If you like to use your calculus, let's use your calculus. So with your calculus, you know that your product of inertia is given by, okay, what is it? It's x, y, dA, isn't it? It's x, y, dA. We are not talking centroidal, we are just using calculus. So if you are using calculus here, let's put our area element. Our area element is a small area element, which is dx thick, like we saw at that time. We also have its height. Its height is dy thick. So this is basically x, y, dx, dy. X, y, dx, dy. Then we integrate away. So for us to get our product of inertia, that will be, in fact, this is actually a double integral. Now that we've resolved it this way, it will be xy dx dy. Just for ease of reference, let me write this as yx so that we notice that we are integrating that first. From where we are integrating with respect to x from 0 to b, then we'll integrate the outwards variables last. That's from 0 to h. So I think you should be able to see now that this is your 0 up to h multiplied by y. What's in there? That's x squared over 2, right? dy. This x squared over 2 is from 0 up to b. Then when you have done that, you can proceed by doing what? By taking out our x squared over 2, because it's now a constant. We've finished the integration and we can apply the limits. So we will have half of b squared again. What does it multiply? It multiplies just the integral from 0 up to h of y with respect to y. And I think you can tell that this is b squared multiplied by a y squared over 2, this time from 0 up to h. So that also gives us another h squared over 2, which is a quarter b squared h squared. So in the end, you will notice that method, whichever method that you will use, you will get your quarter b squared h squared. So for your products, just remember to use your area element in this format. That summarizes the product of inertia. So now we have a tool, guys. We now have a tool. We have 3 tools. We have a moment of inertia about the x-axis. We have a moment of inertia about the y-axis. And we have a product of inertia. These three, the moment you are used to calculating these and you now know how you can get them, especially now that we'll be using tables, then you are good to go. You can actually find any principal axis and principal moments. However, the stages that you will take are going to be quite mathematically intensive. Remember, the physics was done and we actually finished physics when we were studying the basic, those moments, the introduction to the moments. As you can see now, this is from the time we discussed centroids, all we are doing is engineering the mathematics. So when you engineer the mathematics, you can actually come up with different sets of systems which you can use to analyze. So as you can see now, we are just delving on focusing on the math. So for us to then investigate principal axes and principal moments, we need to simply identify a set of axes, which are the principal axes in this case, and then later on we'll actually use any other system of axes. A set of axes to which we convert our normal moments of inertia. What are we trying to say? We're trying to say in the XY axis, we have these ones, Ix, Iy, and Ixy. The moment of inertia and the product of inertia about the original X and Y axis. What we want is to find the moment of inertia and the product of inertia around or about a new set of axes. And we are starting to investigate the principal axes. The principal axes are the axes at which we can get that maximum and the minimum moment of inertia. So these are the X prime, Y prime axes. What is the first thing that we need to do for us to find the I, X prime, and then we find the I, Y prime, then we find the I, X prime, Y prime? What we need to do is to relate the new axis to the original axis. Why? Because we know how to do this one. So the moment we relate the new axis to the original axis, then we can just convert according to the system of the old axes. Okay, so let's now figure out the relations. The text there in figure 9.17 is simply just telling us the orientation of this body and the orientation of the axis of the body and the area element. So what are we trying to do here? In this figure, we have some area A as usual. This is an area which we have found, and it is located in the XY plane that is usually given. So what we want to do is to simply interpret its moments of inertia according to a new system of axes, which are the X prime and the Y prime axes. How are these axes related to the original axis? The relation can be found by finding the coordinates of the area element. The same thing that we did, still remember? The same thing that we did when we were here. What were we doing? We want to find this new moment of inertia with reference to the what? To the centroid. So all we did was to just relate the original axis and their locations to the new axis and their locations. So that's exactly what we're doing in this exercise. So let's relate the X prime to the Y and the theta and the X. The Y prime to the Y and the theta and the X. Right, so the new axis is oriented at an angle theta from the original axis. That's the first and most important point. Now, the area element is located at our X and Y positions on the original axis. Then we're done. The next thing is our relation between the parameters. So in the new system of axes, our area element is located at an X coordinate X prime. It's located at an X coordinate X prime. The Y coordinate is Y prime. For what? For the area element. So we're good now. So how do we relate this one? We can just use the geometry. So this X prime is obviously some distance from this point, right, to this line here that has been used to denote that distance, right? And we should add a second distance to get to dA. So in other words, we need to first find this distance, then we find this second distance, and we've found our total X prime variable. Using triangle O, let's put this one as a P and a Q there. Using triangle OPQ, you can tell that the hypotenuse has a projection in this direction. And the projection of the hypotenuse, which is X, is actually X cos theta. So that's our first step towards the area element in the new system of axes. Then if we use another triangle, QRS at the area element, let's label it with maybe a different color. If we look at that triangle has a hypotenuse Y. That triangle has a hypotenuse Y. That hypotenuse has a projection on this axis, but also another one on that axis. So the projection on the x prime axis is actually y sine theta. Why? Because this theta is the same as this theta. So you can use your basic math to figure that out. This means that we now have our full distance. The x prime is given by the projection for this one, which is x cos theta, plus the y sine theta. Therefore, we have a definition of x prime. X prime is equal to x cos theta plus y sine theta. By the same method and the same steps, if you want to find the vertical orientation, which is the y prime, all we need is the distance from point R, right, to point Q. Then we have a total distance. Then we subtract point P to point Q. That way we can easily find y prime. Therefore, y prime is equal to this distance. So if I could draw a parallel line, this distance, which is y cos theta, subtract this distance, which is x sine theta. So that's our y prime. Y cos theta minus x sine theta. So now we have fully found a conversion system, right? We have fully found a conversion system. We can now relate the new axis to the original axis. That makes life easy for us. So if we have that, then why wait? Let's jump and calculate the products and the moments of inertia. So in the first equation there, let's call it equation 1. In equation 1, what we are doing is to just plug in the values for us to find Ix prime. Ix prime is the moment of inertia about the x-axis, which is the new x-axis, because we said that's what we want to find. So that Ix prime is given by the integral of y prime squared dA. I think you know this from the formula. What is y prime? What is y prime? We said y prime is y cos theta minus x sine theta. So that is our y prime. Y cos theta minus x sine theta. So we now have our y prime. Let's expand the bracket. Let's expand the bracket. We have y squared cos squared theta. That's the first term. So y squared cos squared theta. The cos squared theta is a constant, so it's outside the integral. The y squared stays inside the integral. So we now have y squared dA. The second term, minus 2xy sine theta cos theta. Minus 2 sine theta cos theta are constants. We can take them out. The xy are still variables, so they are integrated. Then the last term is plus x squared sine squared theta. So that's sine squared theta outside the bracket, x squared in there. So we now have some equation number 2, which is the expanded version of equation number 1. Now, if you look at these parameters, do you notice that there are some things that are familiar? The first is y squared dA. What did we say y squared dA is? This is basically your moment of inertia about the x-axis. For that reason, the first term in the solution is Ix cos squared theta. How about this term? That's your product of inertia. We discussed that today. So we take our product of inertia and we write it using the symbol. Our 2 sine theta cos theta still remain in the equation. The last one is obviously our Iy, and that is what is there. And then we multiply by that sine theta that we had there. So we now have our equation 9.15 fully describing the moment of inertia in the new system of axes as a function of the moment and product of inertia of the original axis. So this is cool because you can convert your system into any set of axes, any system of rotated axes, as long as you carry out this transformation. So the good thing is now you already have this, right? All you need are what? Are the values of theta. And you only need the Ix. It's either you are looking for the moment of inertia, and you then have to find your what? your Ix and Iy and Ixy. These ones, Ix and Iy, we have used the parallel axis theorem with tables, with the integral, so we've got all the tools. Product of inertia with the parallel axis theorem and with the integrals. So basically, you can find your moment of inertia about the x-axis, which is the new x-axis, or given this one, you can find theta and the reverse. So this is applicable in so many ways. So basically, that's how you would relate your Ix prime to the original axis. The same applies with your Iy prime. If you carry out the same mathematical formula and stages, you should find this. So let me just challenge you to also see where these things are coming from, isn't it? So you can carry out this calculation. You know that your Iy prime is an integral of x prime all squared dA. Your x prime all squared must be a square of that. Then you identify what you need to in order for you to come up with, equation 916. Now that you have 916, you can do the same and you can get 917 for the product of inertia, just because your product of inertia, x prime, y prime, is given by your integral of your x prime, y prime, dA. So you have your xy and your y prime already, and then you just put them into that equation, expand the bracket, and see that you must get this equation 917. Now we have the moment about the x, about the y, and the product of inertia for the new system of axes, and we know that we can relate them to the original axis in those three equations. Now, as you can see, our equation was long and it had a lot of things, so mathematically you can make life a little easier for yourself. So in this slide, we still have the same system here. I just put it for reference. What we want to do is to simplify the equations from the previous stage. So for you to simplify the equations for the previous stage, this means you need to apply the double angle formula. You need to apply the double angle formula. So on which equation are you applying the double angle formula? For the equation for Ix prime, Iy prime. So both, in fact, all three equations, you need to apply your double angle formula. So let's just try the double angle formula for the first variable. Then you can repeat the same for the next. Right, let's try and make this tiny for the sake of space. So the double angle formula for your cos, what does it say? First of all, you can use some trig ratios. So we know that your double angle formula, cos 2 theta, must be equal to what? Cos squared theta minus sine squared theta. Then you also have the trig identity. Remember, what are we trying to get rid of? We are trying to get rid of, in this equation, of this cos squared theta. We are also trying to get rid of that. Okay, so we also have another ratio which says 2 sine theta cos theta. I think it's what, sine 2 theta, isn't it? Sine 2 theta should be equal to 2 sine theta cos theta. Then it means that you also have that equation which says cos squared theta plus sine squared theta is equal to 1. Right. So with these three trig relations or trig identities, we should be able to now find the trig identity where we can replace our cos squared theta with the 1 plus cos 2 theta, all divided by 2. The same applies for sine squared theta with a 1 minus cos 2 theta, all divided by 2. So let's plug that into that equation. The equation for Ix prime was, or maybe let's do it here actually. Let's take that off. Ix prime, we have the equation now, and we have those trig identities. So let's plug in. So this is our Ix. We are multiplying this by, what is that trig function, cos squared theta? So cos squared theta will be half. So if we just simplify this fraction, that will be half plus cos 2 theta over 2. Half plus cos 2 theta over 2. So we'll multiply this by half, so we can actually divide by 2, and then plus Ix cos 2 theta over 2. Or maybe let me just put it here. Right, so we're happy for the first term, which is this one. We are subtracting a second term, which is Ixy. What is 2 sine theta cos theta? We already wrote that as sine 2 theta. The last term is a plus, and it's an Iy. Sine 2 theta, we said that's 1 minus, isn't it? So we'll have a half, right? A half minus a cos 2 theta over 2. So that will be over 2 minus Iy over 2 cos 2 theta. So if we then group these terms, which are just fractions, we can take out the half. So in the end, we just have an Ix plus an Iy divided by 2. Let's look at the second set. This is Ix over 2 and Iy over 2. So both of them are coefficients of cos 2 theta. So we can say plus an Ix minus an Iy. This is all divided by 2. And then we multiply by cos 2 theta. And then the last term is a minus Ixy, which is sine 2 theta. Nothing changes there, so we're happy. Sine 2 theta. So through this mathematical conversion, we have eliminated a lot of things. X prime. By the way, this is now, you guys, this is your thing now. This is now engineering. The science and the physics, we finished it many years ago. I don't even know what I'm still doing here. So the engineers, this is your time to shine and enjoy, because this is your thing. This is your thing. You take something that was so basic as the moment of a force, then you interpreted it into an area and you denoted it a first moment. Then from the same principles, you analyze some other forces that have certain parameters, and you came up with the second moment. That second moment, you've just discovered, this second moment, we can also find, use the parallel axis theorem. We can also use that system to that moment to calculate a product of inertia. So we have the equation, we know its physical meaning, so why not take this further? So it's very exciting to see that you can actually make use of these steps, and then you can use it in real engineering stuff. So that's our equation from our solution earlier. I will just delete this. So in the end, we actually have this function. We actually have this function. This function is what we see at the top there. That's your Ix plus Iy divided by 2. This is your Ix minus Iy over 2 multiplied by the cos 2 theta. This is your last term, Ixy sine 2 theta. This is therefore a reduced form of your equation. And these 2 theta values are representing what? The 2 theta values in your new system of equations. So we basically have that equation 918 by the same mathematical form. You can come up with 919. You've seen how we've done it here. Just make use of these so that you can also come up with 919 and 920. That way you now have a full definition of the moment about the x, the moment about the y, and the product of inertia in the new system of axes. And all of these are in terms of 2 theta. But then the engineers, when they looked at these equations, they discovered there's something special about these equations. These equations actually have something like an x cos theta and a y sine theta, for them to realize that this looks like parametric equations of a circle. Do you still remember parametric equations of a circle? You've got a circle, right? It's in the xy system. That's your x and y. Right. In actual fact, maybe the y-axis will be somewhere there. Right. So let me just actually do it this way. The y-axis will be somewhere there, and the x-axis will be somewhere there. So this will be x is equal to a. This will be x is equal to a right here. X is equal to a, and this will be y is equal to b. You will notice that if you use a system of parameters where you are looking at your x and your y from some origin, then you can define your x to be equal to an r cos theta and your y to be equal to an r sine theta. So that's if you have something like that, and that's your theta. So when you look at the similarity of these, you'll notice that 918 and 920 or 919 and 920 can actually be put together. So this is what brings about this slide. So what are we now transiting from? We're now transiting from, we just started with the product of inertia. Then we moved to the moments of inertia and the product of inertia for a new system of axes. Now we are in the process of transforming into so that we can find the minimum and the maximum moments of inertia, which are the principal moments. That's what we're trying to do now. This is where these circles come in handy. Now when we look at these equations 921 to 924, these equations are basically breaking down the math that we already had before. So we are advancing from what we had before, and if you look at equation, this equation, it's just a build-up of summing up. So if you add these two, right? So let me remove this material. You can always scroll back. Let me remove this, delete. So these were just derivations, so I think it's not really necessary. Right, so now that we have all this space, if you look at this equation and you add it to that equation, what do you get? On the left hand side, you get an ix prime plus an iy prime. On the right hand side, what do you get? You get this plus that. So that gives you an ix plus iy. This is half, that is half, that makes a whole, right? This part here gives us an ix minus iy over 2 cos 2 theta. This one is a negative, so if we're adding them, we actually get a 0. The same applies for the product of inertia. So this equation is just a consequence of adding 918 to 919. And as you can see, this basically just is the polar moment of inertia. And the polar moment of inertia is just the same, right? It's just the same whichever axis. So this is basically equation 9.21, where we have added the moment of inertia in the x prime axis to the moment of inertia in the y prime axis. It's one and the same. If you sum them, you get the very same value. That's cool, isn't it? That's very interesting. Because in the other axis, we said one is getting small and the other is getting large. So it's actually exciting. To some extent, can I just theorize here, right? Just because it's exciting. Don't you think this is some form of the principle of conservation of mass? Isn't it in the linear system, right? Mass cannot change, right? The amount of substance in a material cannot change if we're just analyzing. We're not destroying the object. We're just exerting some forces on the object and so forth. In the rotational system, our rotational analog for mass is what? Is our moment of inertia. So to some extent, this is like a principle of conservation of what? Of mass. We cannot lose material if we're just applying some forces onto an object. Well, that's just what I would like to read about and think about, but it's immaterial. But what actually connects these equations are the equations, the mathematics which we added, and the polar moment of inertia. This is what connects these two equations. So 9.21, we're happy. Then equation 9.22 is just a consequence of the parametric equations of the circle. It's just a consequence of the parametric equations of the circle. So how would we arrive to that equation? Now, if you look at the equation 918, and then you look at the equation 920, for instance, equation 918 and equation 920, their right-hand sides have something very common. There is an ix minus iy over 2 cos 2 theta. But at the bottom there, we have an ix minus iy over 2 sine 2 theta. If we had a way of squaring these things and adding them, you can actually eliminate these angles. If you look at the product of inertia, the same applies. If you have a way of squaring these and adding them, they eliminate the angles. So in other words, this next step is simply a process of eliminating the angle theta. So to eliminate the angle theta in equations 918 and 920, one can come up with the following. On 918, for us to first rearrange it to look like 920, what we will do is to move this to the left hand side. Let's move that to the left hand side. So what we have is an Ix prime. So let me zoom in and write smaller caps. So we have an Ix prime minus an Ix plus Iy over 2. These are now on the left hand side. On the right hand side, we will have Ix minus Iy over 2 cos 2 theta minus Ixy sine 2 theta. So this is our equation. Let's just call it, okay, it already has a name. Let me call it star. That's our equation star. At the bottom here, we have our second equation. I know it has a name. Let me just name it star star. So what we see between equation star and equation star star are these parameters, where the coefficient of the trig function are the same. So for us to do the elimination, we can just square these equations and add them together. So equation star squared basically squares the left hand side. So we have Ix prime subtract Ix plus Iy over 2 all squared. This is equal to, let's square that very long equation. So I'll try to write in as small a set of caps as possible, just because of my space. I should have created more space, but let's see what we can do here. Ix minus Iy over 2. This will be all squared. Then we square cos 2 theta. We will get the product of both, so that will be minus 2 times Ixy. Then we multiply this by that Ix minus Iy over 2. Then we multiply the trig functions. So that will be sine 2 theta cos 2 theta. Yay, we have just one term to go. Then it's a plus Ixy squared multiplied by sine squared 2 theta. Multiplied by sine squared 2 theta. So we've just expanded the bracket, right? So we've got the first term, which was Ix minus Iy over 2. It's squared. The cos 2 theta is squared. Minus 2 multiplied by the two terms. So that would be Ixy. Then I'm just putting the i's on one side, so next to each other. That's why we have Ix minus Iy over 2. Then we multiply the sine, the angles, the trig functions, sine 2 theta by cos 2 theta. The last term is just a square of the Ixy and the trig function. We now have 3 stars. Let's do the same for equation star star all squared. That is the product of inertia squared. What does it give us? This equation gives us Ix minus Iy over 2 all squared multiplied by sine squared 2 theta plus this time 2Ixy multiplied by that bracket Ix minus Iy over 2. Then we multiply the trig functions, sine 2 theta cos 2 theta. Happy days. The last term, Ixy squared cos squared 2 theta. Now we have equation 4 stars. It's becoming messy now. I should have just used ABC. Okay, we now have equation 3 stars and equation 4 stars. Let's look at those parameters which we said will obviously now help us to eliminate the trig functions. So if we have this first term. This first term that we've just put a blue boundary around, it will be able to add up. So if we add equations 3 star to equation 4 star, that first term will remain squared. The sine squared theta and the cos squared theta will add up to 1. So in actual fact, we can just what can we do? Okay, the coefficient is the same. Okay, the coefficient is the same. So this equation remains as the coefficient when we add them up. So we're happy with that part. Second part is this long term here. So it's a minus at the top. We have 2Ixy, that difference divided by 2, and the product of the trig functions. In this case, it's a plus. In this case, it's a plus. So it's plus 2Ixy, the difference divided by 2 of the moments of inertia, then the product of the trig functions. So if we add these two, they disappear. The last term, we have an Ixy. So let's make it in what? Black? Yep. So that's a plus. And then that one. So as you can see, the coefficients of these squared forms of the trig function are the same. So we can actually factor those out. So this means 3 star plus 4 star. This means 3 star plus 4 star. 1, 2, 3 plus 4 star. 1, 2, 3, 4 gives us the following. On the left hand side, we just have Ix prime minus that sum. So we have Ix prime minus that sum. Ix plus Iy over 2, all squared. Let's do that again. Ix prime minus that sum over 2, then all squared. So we are happy to have it written in this way. This is equal to what? We said the blue terms have the difference term as the coefficient. So that's our Ix minus Iy over 2 all squared. And we know that here we'll just have a 1, which is the cos squared 2 theta plus the sine squared 2 theta. So these coefficients are what will remain. So we're happy with that part. The second term, we said it adds up to 0. We're just adding these two equations. Remember, it's plus. So they add up to 0. The last term, we have an Ixy squared as the common term. So this means on the right-hand side here, we can now add an Ixy squared as the common term, and it's also multiplying a 1. As you can see, we now have equation number 922. As you can see, we now have equation number 922, where we are just summing up the moment of inertia about the new axis minus this sum of the moments of inertia of the original axis divided by 2, and we squared that. Then we add the product of inertia. What happens to my product of inertia? What happened to my product of inertia? It's the left-hand side of this, so I missed. My apologies. So plus the product of inertia, Ix prime, Y prime, all squared. So this term was missing because I had left it. So that's the left-hand side of that part. And then on the right-hand side, we now have the same, which is this term squared plus that term squared. For this reason, we can actually plot a circle whose x-axis is Ix prime, minus whatever center point of that circle, right? Plus y minus b, where this is the y-axis, which is the product of inertia, right? Being equal to r squared, where all these add up to just the radius of that circle. So you are moving from some geometries that you used to come up with the first moments, then you came up with the principle of the second moment, Then you're now using those second moments to find some other variables which are in another system of axes. Then you come back to creating a geometry so that you can find these values easier. So it's very exciting. Right, so we now have an equation of a circle. What we are just trying to do here is we want to conveniently and easily find maxima and minima of moments of inertia for a particular orientation of the axes. So because of that, we needed to carry out this transformation mathematical analysis. Now that we have that in place, this is an equation of a circle like we discussed earlier. So this is our x-axis, which is the Ix prime. So that is our x-axis, which is the Ix prime. Then our y-axis, we said, is the what? Is the product of inertia. Then that's our product of inertia as the y-axis. Now that we have all that, then the next thing is the center of this circle. The center of this circle is given by this let's say a sum term, a total sum term. So it is given a special variable known as the I average. It's given a special variable known as the I average. So that I average is the center of our circle. So from the start here, we have a circle whose center is located at I average. Then our R, our radius. We said our radius is this term. We said our radius is this right-hand side term. So for us to just find R, we would have to take a square root. So the square root is now the square root of all this that's on the right-hand side there. That's why we have this square root. If you are to plot the actual numerical values of the moments of inertia, this radius will actually calculate to this term. This is cool, right? This is really deep stuff, right? Maybe for me, maybe for you it's easy, right? But this is really, because now it means, imagine, with a very complex engineering equation, all you just need is to plot a circle with these parameters. If you plot a circle with these parameters, you just calculate your original moments of inertia about the x and the y axis, and then the product of inertia, then voila, you can actually find moments and products at any other orientation or set of axes. So it's very exciting. So what we have done was to plot for what? For Ix prime. And we now know that we've got that average value. And how can we get a maximum value? For you to get a maximum value, all you need is to add this average value plus this radius. The radius is the same even when it's there, isn't it? So all you need is to add this radius, then you get a maximum value. Or you subtract this radius from the average value and you get a minimum value. In other words, you can actually easily calculate minimum and maximum values of the moments of inertia. And therefore, this circle can only sit at a certain position, right, in this set of axes for a certain problem. Therefore, basically, that is what you do with the x prime. Excuse me, this means that if you would carry out the same mathematical analysis, but this time, instead of you starting with Ix prime, you start with Iy prime. You would come up with an equation that has that looks something like this. So that would be part of your solution, but that equation would have some properties that are shown in part B of this diagram. So this diagram is the same type of a circle that you would get. Remember, the mathematical steps would be different from the Ix prime steps that we took. So in the second circle, what you just have is the Iy prime as the original axis. Why? Because, as the horizontal axis. Why? Because from our analysis, you can tell that that is what you would take to the left-hand side. So you would have taken this to the left-hand side, and this one would be your x variable. So in that case, then you would have a circle, but its x variable would be the moment of inertia about the y. Then your product is still the vertical axis. Your average is still calculated from the origin there, and you just use some similar equation. The only difference would be for whatever Ix that you got if you had a positive product of inertia. In the second case, you would have a negative product of inertia. The product of inertia can be positive or negative. The only ones that cannot be negative are the moments. So that's why they are always, or these are always, on the right hand side of the y-axis. So with these plots of I, of the product of inertia in the new axis versus either Ix or y prime for different values, you can then calculate your minimum and your maximum moments of inertia. Equation 924 is an exciting rephrasing of this equation, because for this equation our b is always equal to 0. That's our starting point for our calculation. Why? Because we said our products are either positive or negative. So our b is 0. So in this case now, equation 9.24 is basically telling you the very same thing that we wrote in equation 922. That our Ix prime minus I average, this is your I average, then plus this product of inertia give you an R squared. They give you an R squared. So this, my dear friends, is the principal axis and principal moment theory. This is the principal axis and principal moment theory. What are the principal moments? We say those are the maximum and minimum. So equation 9.26 just gives you, it's just rephrasing the very same thing. It's just telling you that for you to get the maximum moment of inertia, you need to just add the average plus the radius. For you to get the minimum moment of inertia, you need to subtract the radius from the average moment of inertia. These minimum and maxima are the principal moments of inertia of the area about the origin O. Those are the principal moments of inertia of the area about the origin O. So if we want to find those principal moments which are the maximum, look at where they are located. Look at where they are located. In this diagram, where can we find them? We say this one is I min, this is I max. In the other diagram, this is I max, this is I min. These are all located at the abscissa. These are all located at the product is equal to 0. In other words, we can look at the equation for the product and equate it to 0 so that we can conveniently see if that equation is true. So let's remove that and equate this equation to 0 and see if that is actually true. So this equation, if we would equate it to 0, this means that on the left hand side we have a 0 is equal to all those terms, right? So let me just say all these terms are equal to 0. Now if we are to take our second term to the right hand side, we would have our Ix minus Iy over 2 sine 2 theta is equal to minus Ixy cos 2 theta. Divide both sides by cos 2 theta. Divide both sides by cos 2 theta. What do you get? These will cancel out, and in the end you have a tan 2 theta. So if we are to take this to the right hand side, we would end up have a tan 2 theta being equal to what? Minus, this 2 is now at the numerator, so that's minus 2Ixy. This is now divided by what? By Ix minus Iy. Divided by Ix minus Iy. So that is why they then call it the 2 theta at the maximum. The 2 theta at the maximum or the minimum. So at those two theta values, remember, if we have a negative tangent, our tangent is negative in 2 quadrants. So if the value is what we are looking for here, then it means that we actually have 2 values at which we have a minimum. So this is the equation for the angle, which is the angle at which that original system of yours that you had, if you would tilt it towards, then you can actually find the minimum or the maximum moments of inertia of the system. as you can see, as far as what we need to find is concerned, the most important things are finding this, that, and that. The moment we have those parameters, we can find literally everything. So that basically summarizes the principal axis basic theorem. This equation is just adding on top. It's just the same thing. We know that I max is equal to I average plus R. So this was our I average. I think you still remember that. This was our R from what we put on the right hand side of the previous equation. So basically that's principle number 2. So let's apply it then. Principal axis and principal theorems, example on question number 989. So for the angle cross section indicated, determine the orientation of the principal axis at the origin and the corresponding values of the moments of inertia. So what we just want to find are the principal axis, the orientation of the principal axis at the origin, which are angles. So how do we do that? We know that the principal axes are found at what? At that tan 2 theta m, isn't it? So we know that all we want is to find the orientation, which are the angles, right? So from our equation, we know that tan, let me use this and make it a bit back to what we had, right? So we know that we have tan 2 theta at that maximum or minimum values that we're calculating. This is equal to minus 2ixy over ix minus iy. That's what we know. Now, how can we find these ixy and these ix and iy? We have a section, right? The good thing is, do you still remember that in our tables had the centroids, and our tables also have radii of gyration, and they have the they have the moments of inertia. So as far as this and that is concerned, we can actually consult our tables. So let's say we've consulted our tables and we found that ix, these are actual numerical values, so let me just give them some constants. Ix is equal to a inches to the 4, iy is equal to a to b inches to the 4. These are all in inches, so that's why I am referring to it in its system of units. By the way, you need to always be particular about units. And if you do a dimensional analysis, you'll actually see that here we have a product of inertia, so the units are consistent. Now let's look at the Ixy. So the Ixy is what can be a bit of a tough time for us, especially if you are just still looking at this topic. So that is obviously something that we can recall from the centroidal Ixy plus x bar y bar a. Still remember this equation from the original definition of the product of inertia. So now it means you need to just sum them up, isn't it? Because we know that from basic principle, this is our equation in actual fact. So we need to basically sum everything up. So what are we summing up? We are looking for the product of inertia of this. The product of inertia of this. And we're going to add it to the product of inertia of the other shape. So maybe let's make it red. Right. So this is area number 1, this is area number 2. Right, the centroids of these areas are seen, and we can see that they're symmetric, so this will easily disappear. So in other words, for your first term, you would say your Ixy would be equal to the x1 bar y1 bar area 1 plus x2 bar y2 bar area 2. Right, so I think that one is more of a straightforward calculation. Just remember now, this angle ion, do you notice its orientation? Its orientation is rotated. Usually angle ions are given in this orientation. In the, should I call it the textbook? Yes, in the textbook or the data sheets. So if it's given in this orientation, it has some y section or axis, and its x section axis is given as such. This means when you are interpreting both the moments and the products, the moments of inertia and the centroids, you now need to refer to the system that you have been given. So in other words, you are now thinking with your head. In this case, it will have something rotating. You should actually see a longer side. There must be one side which is longer for usually these sections. So maybe it looks like this. So the longer side will be obvious. So when you look at this section now, you should be able to tell, okay, when I'm looking at my, for example, let's say it's originally like this in the textbook. Let's say it's originally like this in the textbook. When I'm looking at my section and I'm calculating what I need to find, my centroid according to the section is measured, let's say from there. They tell us that this is the what, this is the y bar. And then they tell us that this is the x bar. Am I doing things right here? Okay, let's assume. Let's assume. Right. No. This is the x-axis, right? So let's do things right. This is the x-axis. So maybe let's say that's your y bar, right? This will be your centroid, and that will be your x bar. Right. So when you have been given these parameters, right? What's important is for you now to convert them so that they look exactly like what you see in your diagram. When they look exactly like what you see in your diagram, in other words, now you can tell, okay, what I actually have in my diagram, if it's exactly in the same orientation as the textbook, my Ix is the same as the Ix that we are trying to find. But if there is a flip, like this time where the x, if we are to draw this xx section, we know that it lies in the shorter leg, parallel to the shorter leg. Look at where it would lie. This is where the xx plane or line would lie. This yy line, we know it's parallel to the longer side. So it would lie in this direction. So that would be your y, let's do it this way, y line. So already there is an inversion of the reference points or reference lines or reference axes. So you need to take care of that. So once you have found your centroids, by being careful with what we've just discussed to make sure that you are referring to the correct references to find these values, then you now have your product. Let's call it C, and it's in inches to the 4. So therefore, now for us to find our angle, let me just delete all this. For us to find our angle, then we can now say our 2 theta m. Our 2 theta m is actually given by the arctangent of that minus 2 Ixy. Ixy is C, isn't it? Inches to the 4 divided by Ix minus Iy. We said it's A minus B. These are in inches to the 4. The inches to the 4 cancel out. We have the dimensionless ratio there, and then we can find our angle. It's maybe let's just call it d degrees. That's 2 theta m. So basically it means that your theta m will be half of d degrees. There you have it. You now have found, by the way, you will have the orientations. Please just refer to your textbook, the orientations that have been given here. You want to find the orientation of axes. So obviously if you have an axis, you've got an xy axis. So this is for your x-axis. This theta that you found, if it's 20 degrees, for example, let's say it's 20 degrees. If we are to draw it relative to the original axis, it will be here. This is the angle. The angle that we were discussing earlier on. Obvious, the other axis would be 90 degrees from there, which would be y prime. So basically, those are the steps that you would take to find the orientation of the principal axis at the origin. the corresponding values of moments of inertia. Now the corresponding values of the moments of inertia. These are the moments of inertia in the new system, right? These are, so let's call this part A. Part B is an exercise in which you are now calculating so this is now part B, and let's just write it like this. So you want to find, in part B, you want to find Ix prime and Iy prime. Did they say moments? Did they say product? Moments of inertia. Okay, fine. So you just want to find your Ix prime and your Iy prime. So that's what you want to find. So which equations? We have plenty of equations. So one way is to actually plot this circle. You can actually plot this circle because you have these values, isn't it? You have these values. So you can actually plot that circle that we had. We said this circle is a circle in which we have an x and a y axis. The y axis is the product of inertia. We can actually use the original since we've calculated them. So this is our Ix and the Iy. Now on this circle, we already had some values that we found, right? We have some values that we found. From this Ix and this Iy, we can tell the center value. What did we say the center value is? It's I average. I average is equal to Ix plus Iy over 2. So you now know its location. This is actually A plus B over 2 according to the variables that we have here. Now you have its location. How about the moment of inertia? The moment of inertia is what? Is A. So Ix would be A. So let's assume that it's at this value. That would be your Ix. So therefore, your Ixy will be there. So that would be your point. Let's call it point A. So this would be your Ixy. And it's equal to what? We said it's equal to C. So it's actually equal to C. Let me remove that and put a C. So that's your C. Let me remove that and actually put an A because we already know it. So we've located a certain point in the calculation. Then our Iy, we know its value, so it's B, so its value will be from 0, obviously. And we said our Iy, if our Ix is here, you would find your Iy at that location. So maybe it's located here, and then this is your negative C. This is your negative C, and this is your Iy. And it's actually equal to B, isn't it? It's actually equal to B. Right, that's your B somewhere there. So if we have our A and our B located like that, right, this means that we can interconnect these two. We can interconnect these two. When we interconnect these 2 points, what we now have is a line which is actually the diameter of this line. And the diameter of this line, it has a radius that we want to find. Now that we found the orientation of the new system of axes, this means that we can find conveniently using the geometry of this circle. We can conveniently find the value of the new moment of inertia. Because we have calculated and we found that, okay, according to this, the angle that we found, okay, I deleted it, we said it's 20 degrees. So this is my hypothetical 20 degrees. So if it's 20 degrees, according to our theory, then we would need what? To move 40 degrees from the original axis. When we've moved 2 times theta m from the original axis, now we have a new set of axes at which we have what? We have that x prime, so let me just call it a prime. A prime and B prime. So this is our new axis. This was our original axis, which was x and y. This is our new axis, x prime, y prime, which is at 20 degrees. So according to this circle, it is actually oriented 40 degrees from this system, which was the original. So we can just use your algebra now. So let me just exaggerate, right? Because what I've just drawn is almost vertical, so it might not resemble what we want well. So I will just exaggerate it and say 40 degrees was therefore something like that. So that was your 2 theta m. That was your 2 theta m. So now that you have it that way, if you want to find the Ix, all you need is your geometry. So this is now your what? Your Ix. So this is the projection of this radius onto the horizontal axis. And you've got your value of your Ix. This means your Ix prime would be equal to your I average plus the projection of the radius onto this axis. So you can do your geometry and you can actually see that if I have 40 degrees there, then what would I have elsewhere? So let me just call this angle alpha. Let me call this angle, come on, good. I want to call this angle alpha. So this would be r cos alpha. This would be r cos alpha. So this way you actually have used the circle. Instead of actually calculating, you've used the circle. Instead of actually using these long equations, you've just used the circle. Because in your calculations, the moment you found your Ixy and so forth, you constructed the cool circle. So if you're tired, or maybe you can actually then, or if you have energy, you can actually punch in values and keep punching in values. Instead, you can just master the construction of the circle, and you use just one equation where you can find this from your equations, and you punch in and you get your Ix prime. The same applies for your Iy prime. You are now finding the projection of the other side onto the moment of inertia axis. Basically, that's that circle. But this circle is actually a circle that was designed by the German scientist Otto Mohr. The German scientist Otto Mohr. So this circle is actually called Mohr's circle. It's exactly what we're doing here when we're building this circle. It's exactly what we were doing here. So Mohr's circle is what can be used to find our principal axis and principal moments. And it, in this section, in actual fact, it better depicts the transformation. So look at this. Look at this. We had this system and we talked about transformation from this original set of axes to the new set of axes. And we said we can end up plotting the moment of inertia on the horizontal axis, the product of inertia on the vertical axis, and finding, using Ix, Iy, and Ixy to find the center, and then we can find this this circle. We can draw this circle and find whatever is not known. Now look at this. Look at this. If we have a system of axes, we can actually see where it lands in the circle using this Mohr circle theory. So check this out. So you've got an area A. That is our area of concern. That area is what we're trying to figure out, and we want to calculate its moment of inertia. We want to calculate its moment of inertia about the x and y axes, which are in black, and we have done that so many times, right? We also want to find its moment of inertia at any other axes that are oriented at some angle theta. Then we want to find its moment of inertia at these principal axes. So in this caption, you will notice that they tell us that in part A, we have an area A with principal axes OA and OB. So these are the principal axes, right? OA and OB. And another set of axes, OX prime and OY prime. OX prime and OY prime. So these are obtained by rotating through some angle theta. So we find OX prime and OY prime by rotating the original axis through an angle theta. We find the principal axis OA and OB by rotating the original axis clockwise to theta m. You know, there's this, I always get myself confused with this counter and clockwise, because counterclockwise is positive, but I'm so used to clockwise, so yeah, please pardon me there. Okay, so part B now is Mohr circle, that is used to interpret what's happening here. Now let's see the transformation. So what's happening here is that the original axes are the x, y axes. For us to locate the moments of inertia for both the x and y axes and the product of inertia for the original axis that we would have calculated using, for example, the parallel axis theorem. when we have found the values, we can conveniently locate them on these axes. So we can just look for the values. If it was Ix is equal to A, then we just look for a distance A all the way from where? All the way from this axis. So we just look for a distance A. We now know that, okay, our moment of inertia in the X, it lies somewhere along the line X is equal to A. Instead of Ix, let me say Ix is equal to A. Then we calculate the product of inertia. Ixy is equal to C. And we know that the product of inertia is along this axis, so therefore, whatever value it is, this means this point at which they coincide becomes the point that describes the x-axis of this axis. Why? Because we're calculating the moment of inertia about the x-axis. So where the x-axis is located is where the moment of inertia about the x-axis and the product of inertia coincide. Now we have also calculated Iy is equal to B. So Iy is equal to B. We know that the B is where? The B is somewhere here, right? So that is I is equal to B. This time is what? It's Iy is equal to B. So this B mark would coincide with the same magnitude, but a different value, which is negative of the what? Of this C. So this would be a positive C, this would be a negative C. So at this point, we find the location of the what? Of the y-axis. If we join these points form a diagonal of the circle. Then as engineers, you take your what? Okay, it's not a protractor. You need not a compass, you need this other compass that has got something that you put your pen on. Hey, I'm forgetting. These are high school instruments. I last used them back in the day. So you've got that pencil, and then you've got your pin, and then you scribe a circle. So this circle of this diameter has been scribbled from just 2 points, and you just join the 2 points, and you were using a given axis for the moment of inertia and the product of inertia to locate the points x and y. Now that you found the points, where can we plot the x and y points for the new axis x prime? The new axis x prime is theta degrees from the original axis. So that theta and that theta will give us a 2 theta. So now we will move and shift our new axis for the x prime. So that would be the x prime axis. So it represents the x prime. And obviously the y prime axis will just fall onto the other circumferential point as long as you join this and that point. So basically that's your new line that represents the first axis, which is the or x prime or y prime axis. Now let's look at the last one, which is the principal axis. Fortunately, this time they actually put the principal axis in the reverse direction. So this actually helps you, because now you know that if the principal axis are at a minus so many degrees from the original axis, on Mohr's circle, we would have to move from the original axis down 2 theta, right? So that's 1 theta there and the second theta there. So that would be 2 theta, and then we now have our new axis that lies on the horizontal axis. So let me just remove my annotation because it's messing up a lot of things. So now that we have Mohr's circle, shown like that, this is how we would interpret the moments of inertia of the new axis. Using point x, we just extrapolate downwards and we find the exact value of Ix prime. Same applies. Using point y, we just extrapolate and we find the value of Iy prime. The same applies when we look at the principal axis. We now can easily find the what? The I max. and we can find the I min. So the principal axes are just representing that horizontal line which will bisect the circle at the minimum and the maximum moments of inertia. So this summarizes Mohr's circle and engineering genius, a way of just finding your moments of inertia, the maximum and the minimum, and moments of inertia in any other orientation of axes using the graphical method. So one last example in this exercise is the use of Mohr's circle. So question 991. Question 991 reads, using Mohr's circle, determine for the quarter ellipse of problem 9.67, which is that diagram, determine the moments of inertia and the product of inertia with respect to new axes obtained by rotating the original x and y axis about the first time 45 degrees and then counterclockwise and then 30 degrees clockwise. So it's actually exactly like what we saw in the example. So let's use the red for the counterclockwise angle. So let me just state the data first so that we easily understand what's happening here. So for part A, our theta to the new axis, system of axis is what is counterclockwise is positive. So I will write plus 45 degrees. And then, so let's say theta for theta prime, right? Then part B, our theta prime for the new axis, another set of axes, clockwise 30 degrees. That's a minus 30 degrees. Okay, so if we are to draw here, I'll just draw on the same axis just for us to easily follow. So we can be safe to just draw this line and declare it the new axis x prime. And this line is at theta prime for the x prime axis. So obviously there we would have the y prime. Then we would have a 30 degrees, so let's make it a slightly smaller angle, a 30 degree, maybe let me just make it purple. It's a slightly smaller angle, so maybe it's something like that. So that's the x-axis, the new x-axis, but it's in the negative, so that's the theta prime. So this is the x prime axis. This is the, okay, we are going below, so my y-axis will be like this. So that's y prime axis. So basically, that is what it means. These are the axes that we have now found. So in order for us to work this out, we need to plot Mohr's circle. So let's plot Mohr's circle. So we know that we can start from the left because it always has a, there are no negative values for the moments of inertia. So this is our moment of inertia axis. It can be moment of inertia about the x or moment of inertia about the y. This is our product of inertia axis. This is our product of inertia axis. This is our origin. Now, obvious. What is the first thing to start with? We need to find the three variables. So we need to find Ix, Iy, and Ixy. Ix, Iy, and Ixy. Right, for those that have been used to their math, when you look at that analytic function, how can you find Ix? How can you find Ix? Right, so let's start with Ix. So we know that dIx is equal to our y squared dA. When we look at that area, can we use the tables? Is there any function on the tables that we can make use of? I don't know if we have something on the tables that has this kind of geometry, because they usually tell us a parabola or they tell us a triangle and so forth. I don't know if we have, so let me just assume that we actually don't. So if we have dIx is equal to y squared dA, then it means that you will need some some strip. So let me use a vertical strip, for example, for this calculation. If I use a vertical strip, my life becomes easy because I will know that my di about the x is actually, what did we say? We had an equation that time. 1/3 of what? Of y cubed dx. 1/3 of y cubed dx. So this means if I have this function, I just need to rearrange it, because I now know that y squared over a squared is basically equal to, excuse me, 1 minus x squared over 4a squared. That's my y squared over a squared. So if I can find y squared, then it's obvious I can just move my a and so forth and find my y cubed. So we're happy. If you want, you can also have a square function here. Since we have y squared, I think it would actually be fun, right? It should be fun. So you can do your math. Anyway, this is a chapter that's before, so you can have fun finding the ix. So let me call whatever value that we get. It's in terms of a, isn't it? So let me just call it, let's say this was what? Let's say p in the x, let's say pa. So that the next one, iy, let's just say our iy is equal to p, then qa. Let's say our product ixy is actually equal to pqra. Right. So remember, I'm just making these up. Your task is to actually calculate these moments of inertia and the product of inertia. Because by the way, this is the biggest deal. This is what we now have. Right, so let me maybe just now interpret this and put it into our diagram. I would like to just give P some value and just say this is 5 AE, and then I'll give Q and say this is 10 AE, and this is what? Maybe 8 A. Let's just say. I can't tell offhand if they should be larger or smaller than each other, whichever way. Right, so let's just say that's what we have there. Now, okay, the IY usually is smaller, so let me just say 1. Let me just say 5. Let me just say 3. Okay, 3A. Right, so this is what we now need to do. We need to plot the circle. At least the first thing that we need to find is the what? The I average. So we need to find the I average. I average is equal to, when we've plotted the circle, I don't know if you use plot or plotted. When we now have the circle and we know its origin, the only next thing that we need to do is to locate an x and a y, right? Is to locate an x and a y. So this is our circle. It's in terms of a, so maybe let's say that's 1, 2, 3, 4, 5, 6. This means that I will have to change. Okay, I don't have to worry about that because that's in another axis. So let's call this 2, 4, 6, 8. Good. So that would be 8A, that would be 4A, that would be A, 2A, 3A, 4A, 4A, 5A, 6A. Right, so this is quite okay. I'll also move -2, let's do that, -2, -4, that's -4A, -6, -8A. Perfect. So we now have a system of axes. So let's find the x position, right? Let's find the x position. The x position is a position for the original axis, and it is located at the moment of inertia and the product of inertia. How about y? Y is also another location, and its coordinates are the moment of inertia about the y-axis and the negative product of inertia. So what is the moment of inertia? The moment of inertia, we said it is equal to 5a. So that's our 5a, so it's located somewhere here. The product of inertia, we said it's an 8a, so it's located at that point. We have now found the point for x. That's the x-axis. Then we now want to find the y-axis position. The y-axis position, and the y-axis position is, we said it's iy minus xy. So minus xy is here, iy is 3a. So it's located there because this is our 3a. So we're happy now. We can join the 2 points and they form 2 radii. Then you can plot your circle. That's a very poor circle. That's a very poor circle. That's a very poor circle, sir. Ah, that's a good thing. Thank you, Mr. Software, Mrs. Software, whatever you are. Right, so we now have our circle. We're now happy with our circle. We know that these are the moments of inertia for the original axis. Now we want to find the moment of inertia for the new axis. We know that the first axis is 45 degrees from the original axis, so we need to find 90 degrees from here. So from here, if you use your math or you use some graphical method, then you need to locate your that's not normal. That's not normal. We need a normal. We need a normal, maybe something like that. There you are. Now you have a new set of axes. This new set of axes has a point there. So this is your x for the first axis and your y for the first axis. And if you join these lines, you've got your radius. What was this angle? This angle is 90 degrees. This angle is 90 degrees. How about the second set? How about the second set? The second set is at minus 30. The second set is at minus 30. So, right. Okay, so let's plot it. So it's almost this. Okay, it becomes 60, isn't it? Yeah, it becomes 60. So maybe let me exaggerate. But it mustn't be 90, right? So let me try it this way. Right. So this is a minus 60 degrees. This is a minus 60 degrees. So since we started there, that's our x prime prime, and this is our y prime prime. Now all we want to do with Mohr's circle is to locate the moments of inertia, because that's what we've been asked for. So that in the end we can say for the let's say for the axis, what is our ix, what is our iy, isn't it? That's all we want to find. That's our iy. So we've got the x prime, y prime axis, and then the x prime prime, y prime prime axis. X prime prime, y prime prime axis. Right, there we are. So let's geometrically find for the ix for this axis. So that would be our ix. This is now ix prime. It coincides with what? Almost 2a. May I please make life easy for myself and just write a 2a. So you will have done the math, isn't it? So this is actually a scale on a graph. You can actually figure it out. So if you extrapolate it graphically, you can find it that way, or else you can actually use these angles. You can actually use these angles because what you have is some angles. You've got this, you know, this is 60 degrees, but you also know that this is 90 degrees, isn't it? That this is 90 degrees. So you can then do your ratios so that you can use maybe an angle alpha to find this r cos what? R cos alpha. So there you have it. That's something like 2a. How about iy? Iy, we just find the y point location. Maybe that's 6.1a, something like that. Then your x prime prime. X prime prime is right here. So maybe that's 6.5a. And then iy is there. So it's also 2a somehow. So you're happy. So that is how you would use Mohr's circle to interpret a system in an xy plane or coordinate into an x prime or an x prime prime y prime prime coordinate system. This implies then that if you are asked for the average, or if you're asked for the maxima, or they say what are the principal axes, then you already know from this circle that you drew that, okay, I just need to locate this intersection. I need to locate that intersection, but you can sometimes not be asked for that. So basically, as you can see, it sums up Mohr's circle. So this is the end of our Mohr circle discussion. In this discussion, basically what we looked at are products of inertia which are used in Mohr circle. So that was our first principle. The product of inertia was defined as basically your your Ixy, which is equal to the integral of xy dA. And you use a square area element to calculate it, which means you will perform a double integration. And then from there we learned of the principal axis and principal moments. We converted a system, we came up with the circle, and we came up with the derivation of the circle. Then we made use of all those parameters to actually solve and find the moment of inertia about the x or the y-axis using Mohr's circle. So it's just now some graphical techniques and plotting it on a graph. So those that like programming, this is a chance. Imagine if you write a program for Mohr's circle, imagine how many engineering problems you can just solve at the click of a button. Look at all those equations. Imagine if you were to be asked to actually find the moment of inertia of a system at a certain orientation of the axis. Look at all those equations. Instead of you doing all that, you're just doing it graphically. So this is a very high-level problem-solving system. It's actually a system. If you were to write it into a program, it's going to solve very complex engineering setups with a few functions or with a few calculations. So this is the end of our discussion of lecture 7. Let's meet for number 8 tomorrow. Have a good day. Thank you very much for your time. Enjoy.